There are a set of rules that can help us establish the oxidation number of every element that occurs in a chemical reaction. The first of these rules is that pure elements are zero. So if you see oxygen, O2, or iron, just Fe, the oxidation state for those elements is zero. The same for chlorine or hydrogen or copper or iodine or sodium or sulfur. Pure elements have an oxidation state of zero. Rule number 2. The oxidation number of a monoatomic ion is the same as its charge. So if you're talking about the sodium ion, you know that it always has a charge of +1. So the oxidation number is +1. The oxide ion, you know, has a charge of -2. So its oxidation number is -2. Chlorine, or should I say chloride, you know, has a charge of -1. So its oxidation number is -1. Rule number 3. The sum of all the oxidation numbers for a compound must always equal 0. Now that's if you have a neutral compound like water or hydrogen peroxide. Always the oxidation number is 0. So if you have a pile of rust, for example, you know that, and we have this formula, Fe2O3, and we're assuming we have this formula written correctly, then we know that the sum of the oxidation numbers must be 0. So we see 3 of the -2 ions plus 2 of the iron ions. So if we solve for that question mark, that will give us the charge of the iron ion, in this case 3 plus. Now if we have this formula, FeO, we know that the charge of oxygen from our rules is going to be -2, and so the charge of the iron in this case must be +2, because the sum of those oxidation numbers is 0. Rule number 4 for determining oxidation numbers. Alkali metals are always +1. Alkaline earth metals are always +2. And that should make sense to you because that is the charge of the ions in those columns. Rule number 5, which will clarify something I did back in rule number 3, oxygen is usually -2. So in these cases, we see 3 compounds containing oxygen. In all of these compounds, the oxidation number for oxygen is -2. So when you have oxygen in a compound, its oxidation number is usually -2. Now that allows you to tell what the charge of the positive oxidation numbers will be, because we know that they have to add to 0. Now, in peroxides, the oxidation number of oxygen is going to be -1. Now, we're going to list here all the peroxides that you are likely to ever see. The first one is hydrogen peroxide, H2O2, and then in this case the oxidation number of oxygen is -1. The second peroxide that's listed is sodium peroxide, and the third peroxide is potassium peroxide. Now, it would be possible for you to see other peroxides than that. However, it is not likely. There we go. Get it back to that slide. Those are the three peroxides you're ever going to see, and those are the only places where the oxidation number of oxygen is -1. Rule number 6. The oxidation number of hydrogen is usually 1+. So here we see two hydrogen-containing compounds, methane and acetylene, and in each of these we see hydrogen combined with a nonmetal, and in those cases the oxidation number of hydrogen is going to be +1. Now, in this last example, which is methanol, both of the hydrogens, or actually I should say all four of the hydrogens, have a charge of +1. The oxygen we know is -2, and that allowed us to calculate the oxidation number for carbon as -1, because with those oxidation states, all of those add together to make a charge of 0. But the thing you have to look out for is if hydrogen is with a metal, such as lithium hydride in this case, or potassium hydride in this case, the oxidation state of hydrogen will be -1 if it is combined with a metal. Rule number 7. Fluorine is always -1 when it's in a compound. Chlorine, bromine, and iodine are usually -1 when they are in a compound. So how do I tell if a reaction that I have is a reduction-oxidation reaction? Well, I write out the equation for the reaction, and then I write down oxidation states of every element in every compound. So once we have done this, and we'll practice this in a few minutes, once I have written down the oxidation state of every element and every compound, I can then look to see, are there any elements that in the process of the reaction change oxidation states from before the arrow to after the arrow. Of course, keeping in mind that loss of electrons is oxidation, we see here that the charge is going to get greater. So looking here, is there anything where the charge became greater? Well, if you look at carbon, it went from -4 to +4. So the charge of the carbon became greater. So that is oxidation. Now remember, the gain of electrons is reduction. And for reduction, the charge is going to get smaller or be reduced. Now in this particular case, oxygen goes from 0 to -2. So the oxygen is being reduced. There is a redox reaction here because the oxidation numbers change. Now here is a second example of a reaction. We have silver nitrate combining with sodium chloride to produce a silver chloride precipitate and sodium nitrate. And if we write in the oxidation states for every compound, here we know we've calculated the oxidation state of the silver is +1 because that's the charge of that ion. The 3 oxygen sum to a -6, so the nitrogen in this case must be +5. Writing in the rest of these, because we know the charges of the ions or we calculate them in some other way, we see that there are no oxidation numbers that change from the reactants to the products. If there is no change in the oxidation number, it is not a reduction-oxidation reaction. This is a particularly interesting reaction. If you take hydrogen peroxide and pour it out onto a cut or pour it somewhere where it will bubble off oxygen, is that a redox reaction? Well, remember, in hydrogen peroxide, the oxidation state of oxygen is -1, hydrogen is +1, and here we've seen the producing oxygen gas, which has an oxidation state of 0, and in the water, the oxidation state of oxygen is -2, and the oxidation state of hydrogen is +1. So, loss of electrons, remember, is when we change by increasing the charge or losing negative charges, losing electrons. So there is a loss of electrons and there is also a gain of electrons. So this is an oxidation reduction reaction, and what's interesting is it is the same element. It is oxygen that is doing both the reducing and the oxidizing. And just for a few seconds, take a look at this reaction. You'll notice that iron is losing electrons and copper is gaining electrons. So the iron's oxidation state changes from 0 to 2+, and the copper's oxidation state is reduced from 2+ to 0. For more practice in assigning oxidation states to different elements in a compound, go to the video where we look at several specific compounds and assign oxidation numbers to each element in those compounds.